Thank you for the introduction. I would like first to thank organizers for giving me this opportunity to speak here. So I will present our results, our experimental results on piezoelectromagnetic effect, in which we control magnetization by an electric field, and I will also show some numerical results using atomistic spin model simulations. Here is the list of our collaborators. So magnetoelectric effect has been already observed in many materials like multiferroics, dilute magnetic semiconductors, magnetic piezoelectric hybrids, and for example, here is electric field control of the magnetic properties in indium manganese arsenide. So for example, here we see electric field induced transition from the ferromagnetic to paramagnetic state in this material, or electric field control of coercive field in ferromagnetic state. And here we investigate piezoelectromagnetic effect in dilute magnetic semiconductor, gallium manganese nitride. So for example, this is gallium nitride host crystal structure with few percent randomly distributed manganese ions. So our material is both piezoelectric and magnetic, because gallium nitride is piezoelectric material, and when doped with manganese ions, it is also magnetic. So our system is highly insulating, because manganese impurity is located in the middle of the gap of gallium nitride. So in fact, manganese kills all carriers, both holes and electrons. So our material is insulating, and manganese is usually in free plus charge state, characterized by spin and orbital angular momentum equals to 2. So we have single ion magnetic anisotropy. So previously we investigated this effect in paramagnetic state of our material, characterized by low concentration of manganese ions. So we apply voltage difference to our material. Here is the z-axis of our material. This is also growth direction of our material, and through the inverse piezoelectric effect we change the thickness of our material. So in fact we change the C lattice parameter, and in this way we control single ion magnetic anisotropy of manganese ions. So we also change the magnetic signal. This is magnetization both for the easy axis and for the hard axis. Hard axis is when the magnetic field is applied along the z-axis of the crystal, and we have also easy plane. Because single ion manganese anisotropy depends on the local arrangement of atoms around manganese. So by deforming the crystal, we change the atom arrangement, and we change the magnetic anisotropy. However, the problem is that we have, in our samples, we have three dislocations, as shown here. This is transmission electron microscopy image of our sample. This is our magnetic layer grown on conducting gallium nitride doped with silicon, and we observe the presence of such threading dislocations. And when we apply voltage difference between top and bottom of our layer, the current will flow through such threading dislocation, and there will be no electric field on our material, and there will be no piezoelectromagnetic effect. So additional dielectric barrier is needed. So this is our structure after some preliminary processing. So we have our magnetic layer grown on gallium nitride doped with silicon. This is conducting layer, and the substrate is sapphire, and we have gold contacts to this conducting layer. And of course we have these threading dislocations in our material, so we cannot deposit gold. So we cannot deposit gold layer here and apply voltage difference here, because there will be current flow through such threading dislocations. Therefore we have to deposit additional dielectric oxide by atomic layer deposition, which blocks the current flow through such our structure. Then we have gold layer. This in fact is capacitor. Yeah? We have one plate, the second plate, and our material acts as insulating material. Then we can apply voltage difference, and we have electric field on our magnetic material. So this is sample processing in more details. So we have this the same as in previous slide. So in fact on top of our layer we have many small capacitors. So we checked every capacitor separately, and only those capacitors characterized by high breakdown voltage are connected in parallel and further studied. And this is the real picture of our layer, these bottom contacts and top contacts. And experimental setup. So we use standard modulation technique, that is, we apply both DC and AC electric field or electric voltage. Usually much larger DC voltage to change the anisotropy, and smaller AC electric fields to detect our magnetoelectric signal. So the sample is placed in squid magnetometer. So we apply AC voltage, therefore we change through the inverse piezoelectric effect, we change the thickness of our layer, so we change also the magnetization in phase with the applied AC electric field. And the changes of magnetization are collected by squid pickup coils, and then the signal is detected by locking amplifiers. This is phase sensitive detection. Here is in more detail. So we apply sinusoidal modulation. So through the inverse piezoelectric effect we change the thickness of our layer. Of course the changes are very, very small. And finally we modulate the magnetization in phase with the AC modulation. And we investigated this effect in gallium manganese nitride, now with higher manganese concentration, about 6%. So now the sample is ferromagnetic. This is standard magnetization as a function of magnetic field. Navy points or blue points correspond to the easy axis, and light blue points correspond to the hard axis. The magnetic anisotropy is very small, but in small magnetic field region we see clear hysteresis loop. The coercive field is about 100 Estet. And the Curie temperature is low, it's about 7 Kelvin. So the ferromagnetism is due to the presence of ferromagnetic superexchange interaction between manganese ions. And we assume that this, because there is no carrier, our sample is insulated, and we assume that the strength of this interaction decays exponentially with the distance between manganese ions. Yes, this is in logarithmic scale. And this is magnetoelectric signal, both for the easy blue points and hard magnetization direction. green point, the magnetoelectric signal is just the difference between magnetization with applied electric field and without electric field. So the explanation is here. This is standard magnetization. These navy points correspond to magnetization without electric field, and blue points correspond to magnetization with positive voltage applied to the top of our structure. So in fact we decrease the magnetization with increasing of the voltage applied to the top of our layer. So the magnetoelectric signal is negative and in antiphase with the applied voltage, AC voltage. The situation is opposite for hard magnetization direction, as shown here. Now we increase the magnetization with application of positive voltage to the top of our layer, so the signal is positive for positive magnetic field and in phase with applied AC modulation. And here is the magnetoelectric signal in very small magnetic field range. We also observe clear hysteresis loop with coercive fields very similar to the one observed in standard magnetization measurement. This is again standard magnetization, and this is magnetoelectric signal for easy axis, and in next slide I will show only the results for easy axis. So we see that the signal is reversed as compared to the standard magnetization and in antiphase with the applied AC electric field. So we were interested if it's possible to control coercive field by electric field. So in order to answer this question, we measured the magnetoelectric signal for few different DC electric fields or DC voltage, and we see that the coercive field does not depend, practically does not depend on the DC electric field. And so because we assume that by application of electric field we change only uniaxial anisotropy, we do not control the width of coercive field. However, the coercive field depends on the AC modulation. We see that by increasing the AC modulation we decrease the coercive field, and for high enough AC modulation the coercivity practically vanishes. So we see that we can control coercive field by AC voltage. And we also observe the switching of the magnetization. This is again magnetoelectric signal. Blue points are magnetoelectric signal for 0 DC voltage. So we can sweep the magnetization from right to left. We can stop, for example, here, or we can stop here. This is done for 0 DC, and then step by step we can change the DC electric field, and we observe the switching of the magnetization induced by DC changes. And the switching is not reversible because we can only switch the magnetization from here to here, not vice versa. We cannot switch it back here. And the switching is observed both for the negative and positive changes of the DC electric field. Of course, at this point it is not possible to switch the magnetization. The explanation is here. So again, this is magnetoelectric signal. We can switch magnetization. We can stop here or stop here. And the switching is possible only at this point. Only at this point when the Zeeman energy is positive, because at this point the magnetization is anti-parallel to the external to the external magnetic field. And by changing DC voltage, we change the magnetic anisotropy, also we change the effective magnetic field acting on manganese spins, what induces the precessional motion of the magnetization, what drives the system toward the equilibrium position, toward the minimum of the Zeeman energy. And of course, at this point, it is not possible to switch the magnetization because the magnetization is parallel to the external magnetic field and the system is already at the minimum of Zeeman energy. To explain this data, the experimental data, we simulated magnetic properties of our system. So we use atomistic spin model simulations. So this is our simulation box. We have gallium nitride host crystal structure with 6% randomly distributed manganese ions, exactly as in the experiment. Our simulation box has about 10,000 interacting manganese spins, and we use stochastic Landau-Lifshitz-Gilbert equation to simulate the precession of each spin. So first we take into account the super exchange interaction between manganese spins in the form of Heisenberg interaction. Up to the interactions are up to the 14th neighbor. So for example, we can have nearest neighbor position of manganese ions, next nearest neighbor position, or more distant neighbors, and up to the 14th neighbor. And we assume that the strength of this interaction decreases exponentially with the distance between manganese ions. We take into account also magnetocrystalline anisotropy. We have uniaxial anisotropy along the c-axis of the crystal. So we modify this uniaxial anisotropy by electric field. We have here a hard axis along the c-axis, and here is the easy plane, perpendicular to the c-axis. And we can control this parameter by electric field. And we also take into account triaxial anisotropy originating from the Jean-Teller effect. So we have three easy magnetic axes along A, B, and C as denoted here. And here is the C-axis of the crystal. This is, in fact, cubic anisotropy. And we assume that this cubic anisotropy is not controlled by electric field. And thermal effects are included in standard way. So we generated this Langevin dynamics. So we generate random magnetic field for each manganese spins, and at every step of LLG iteration. So this random Gaussian magnetic field of mean 0 and standard deviation given by this equation. From these terms we can calculate effective magnetic field acting on each manganese ions and at every step of LLG equation, and then we can simulate the dynamics of every spin. And here are the results. This is magnetization. In blue we have experimental magnetization. I showed these results previously, both for the easy and hard magnetization direction, and red points are the results of numerical simulations. So we can at least qualitatively reproduce our experimental data. Even the small coercive field of about 100 Ehstedt is reproduced by our simulations. And here is the experimental magnetoelectric signal, both for the easy and hard magnetization direction. Red points are experiment, and blue points correspond to the numerical simulations. So again, we can at least qualitatively reproduce our experimental data. For simulations, we use parallel computations. The simulations were performed using graphical processing units and CUDA toolkit. And finally, conclusions. So we observed piezoelectromagnetic effect in ferromagnetic state of our material. We showed that we can control magnetic coercive field by AC electric field, and we can also induce the switching of the magnetization by electric field, and we can describe experimental data using atomistic spin model and Landau-Lifshitz-Gilbert dynamics. So thank you for your attention.
So do you see any particular applications of your result as, I don't know, with reference, for example, to superconductor for magnet structure somehow?
Yes, we can, in principle, we can build, for example, a magnetic memory out of our device, because then we can switch magnetization up and down using, for example, sub-nanosecond electric pulses. But so the next step will be to build such device and to create magnetic memory out of this effect.
Thank you.
Thank you. Other question, please.
I was wondering about the extended defects that you showed at the beginning. You know, what is their origin, and do you know what they are exactly?
Because our samples are grown on sapphire substrate, and because of the lattice mismatch, we have these threading dislocations. We can reduce this thread number of or concentration of this threading dislocation by growing on gallium nitride substrates, for example, by few orders of magnitude to reduce it. Yeah.
Because then you fix the problem by making in some way a condenser, right?
Yeah.
And then, so you overwrite the problem. But that means you don't really care too much for your device that you have this or not.
Yeah, we can use this oxide layer and we can fix the problem.
Okay, thank you.